Okay, we're going to work on this next problem, which is a pretty challenging problem here. But what I'd like you to do is I'd like you to work on this in a group. This is going to serve as a kind of our quiz for today. And so what I'm going to do is I'm going to do breakout rooms here in Zoom. And so for each breakout room, we'll have 4 rooms, then we'll just turn in one quiz per room. And so you'll work as a team of 4 to 5 people trying to solve this problem. And so just work together and try to figure it out. And then you're going to do a room submission. So there are going to be 4 rooms. These are going to be just I think randomly assigned or automatically assigned into 4 breakout rooms. And if you need to switch, let me know or something. I'm not that familiar with how this works, but let me try to create the rooms right now and see if you get into smaller rooms. And then, yeah, okay. So I have 4 breakout rooms, and then I'm going to open all these rooms. Okay, so you're going to be invited to join. And so go ahead and join the breakout rooms and then work with the other people in your breakout room to solve this quiz. Okay, and this is going to be challenging, so you'll have to work together, and then you'll just turn in one. So actually everybody will write it out, but we'll just get 1 submission per room and then write down all your names on that 1 submission. Okay, is that clear? And so work on this problem here together in your breakout room, and then we'll figure out how to submit it later. Okay, are there any questions? Let me see if so the rooms are going to contain between 3 to 5 people, depending on if everybody joins, 4 to 5. I'll keep that into consideration. But see if you can, within your group, be able to solve this. If you can't, you can always post stuff, and I think in the group, I don't know if you have a breakout chat or a group chat, but let's try this out and work on this. I have to take care of one thing here, and then I'll be back in a little bit to follow up on you guys. But this is the problem here. And so try that out. And I'll try to give you hints if you need it. Okay, I'm going to pause the recording right now. Oops. Sure. All right. So the sig figs, that's a bit tricky, Francis. Do we round to 1 sig fig or 3? And so let's take a look at the sig figs here quickly. Some of these, you know, we got to think as far, like this chlorinating solution. Do you think the manufacturer of this is highly precise or not so precise? And it's probably not so precise. You know, if they're solving 7%, that probably means it's anywhere from 6.5 to maybe 7.4%. You know, and so they don't spend a lot of time getting it exactly right on 7. So it turns out this I'd probably say is 1 sig fig most likely. You know, just because when you go buy the chlorinating solution, it's probably got that kind of precision. This 1 ppm is ideal. And so at 1 ppm, I would probably call that infinite, exactly. You know, ideal, we'd want it exactly on 1 ppm, not too high, not too low, exactly. So this is hypothetical here. Our target is hypothetical. This one is 3 sig figs, you know, the density of the chlorinating solution. Well, if the chlorinating solution varies a lot, the density would also vary a lot. So there's a disconnect here because there's only 1 sig fig here, but there's 3 sig figs here. And so a little bit of a disconnect. And so this probably is a little higher precision. You know, I'd say if they had 3 sig figs in the density, they probably had 3 sig figs in the composition. And so it might have been 7.00% chlorine by mass here. and they just didn't do it because these two are connected, you know. And the density of the pool water here, they have to 3 sig figs. The pool water is very little chlorine and very little other stuff in there. Still don't want to drink it, but you know, that's almost like pure water. In fact, pure is close. Pure water is probably a slightly less. To 3 sig figs, pure water is like 0.998 or something to 3 sig figs, grams per milliliter. And so this is still a little bit more dense than that. To 2 sig figs, water, pure water is just 1.0 grams per milliliter. So it depends on how precise, you know, how many sig figs you want in the water, what kind of accuracy you want to. So we'll just take this as 3 sig figs here. 18,000 gallons, this could be infinite or 2 sig figs. You know? Infinite in the sense that if you start off with exactly 18,000 gallons, just one second, I need to answer this. Okay, yeah, sorry about that. And so this could be hypothetical. You know, if we had a hypothetical 18,000 gallon swimming pool, then we can call it exact. You know, if your swimming pool is 18,000 gallons exactly, then how much approximately do you need for chlorinating solution? And so there, in that case, we'd want it exact. But here, you know, the sig figs are a bit ambiguous. And so in a particular problem like this, I like to do this exactly. You know, I say hypothetically, if we had exactly 18,000 gallons, and these were the densities, and let's say the chlorinating solution were exactly 7%, then, you know, what would it be? You know, and then you could have additional sig figs, like 3 sig figs, 4 sig figs, and then round it if you want, you know. I think most people got close to 0.9 liters, you know. And so if it's like 0.9 liters, then we do like, you know, 1 liter or something. You don't want too much chlorine and you don't want too little chlorine. So you got to be careful when you do it. And so since this problem, the sig figs are kind of messed up anyway. I'm not too strict on sig figs on a problem like this, you know, so don't worry about the sig figs too much. I'd like to see more sig figs. What I don't like to see is somebody just give me a final answer to 1 sig fig. You know, 1 sig fig, there's a lot of uncertainty there. And so I want to see more digits and then round it, and then I'll be happy. Okay, any other questions before we leave this? And so that's the end of chapter 3, pretty much. So we're going to the next chapter here. This is going to be chapter 4. Any windows open? Okay. All right, so chapter 4 is an introduction to gases. We're going to cover gases over two chapters. And so this chapter is just the first part. And part 2 is going to come later. It's not chapter 5. Chapter 5 is something totally different. Here's an airbag. So the chapter begins with an airbag. Airbags are pretty interesting. Airbags are really small, actually. And what happens is there's a chemical reaction that gets triggered when one of the sensors goes off. And the chemical reaction is this, I guess that you can kind of call it explosive, but it's a pretty violent decomposition of sodium. This is called sodium azide here, Na3. And it's a solid. They didn't write the states. This is from Scientific American, an article I just pulled off there. And so let's go ahead and write that. here. This is solids. Solids, you know, because everything's all touching. Solids don't take up much space. So the actual amount of space that this takes up is very small. They use 130 grams of sodium azide. Most solids are about 2 to 3 times more dense than water. And so if it's 130 grams, then it's about, you know, 60 milliliters worth of sodium azide, maybe, you know, just rough estimate there. Will produce 67 liters of gas. So you're going from like 60 milliliters to 67 liters. That's a huge expansion, because what's happening is, let's say this is 67 milliliters here. And then we go from 67 milliliters to 60 milliliters. I'm guessing at 60 milliliters. I need the density. If I had the density of sodium azide, then I can figure out precisely how many milliliters, but they don't give me the density here. So I'm just taking a guess that it's about twice as dense as water. And then we got nitrogen here. Nitrogen's a gas, and that is going to produce 67 liters. So the volume expands from 60 milliliters to 67 liters. So that's why this huge balloon here. It only takes 0.03 seconds. So it's a very rapid reaction here. It's kind of explosive, and so this is why there have been deaths, you know, with small children in the front seat, because this really is a pretty explosive reaction, generating a lot of gas, and could generate a shock wave. Sodium is the element sodium. Sodium, the element, is not stable. Sodium element, the element, is very reactive. Sodium is very reactive, and it could cause other side reactions which are violent. It's also not good in your eyes, nose, mouth, etc. And so they add other chemicals. Other chemicals are added to react with any sodium. So there's a second reaction that takes place to kill off the sodium here, which is quite reactive. But anyway, the gases take up a lot of volume because there's a lot of empty space there. And so, let's move on. Here. Gases can be compressed or expanded. This is showing compression. You know, we can push with 2 weights here, or 3 weights, or 1 weight, or no weights. If there's no weights, that's just normal, a volume here. At the particulate level, we're just getting less empty space. You know, we still have the same number of particles, less empty space here. This is called a vacuum. A vacuum is when you, okay, let's say we have no weights on there. We're going to pull the lid up. You pull the lid up, you're expanding the gas. That takes work, you know, to do that, to expand it like that. Work to pull it up. It takes work to push it down. But you're just creating more empty space there in a vacuum. Macroscopic, you know, it's more concentrated here and least concentrated here. The gas is. You know, solids are very dense, you know. Normally solids are more dense than liquids, except for ice. Ice is a very open structure. This is water. You know, these are not compressible. If you try to expand or compress these, it's not possible because they're already touching. And so we have hydraulics for liquids, and solids aren't. This is iron nails, so iron. Iron forms a lattice structure like this, but you know, the simplest unit, the empirical unit, would just be a single iron atom. You know, water forms molecules. This gas, I don't know what this gas is. It's diatomic, so it's probably nitrogen or oxygen or something like that. And there's a lot of empty space. How much empty space? Well, lots. And so therefore, if we mix gases, like say, for example, if I have this orange gas and I add some green gas, there's no problem with mixing gases. But there are some issues though with mixing gases. Sometimes it's not super easy to mix. Let's take a look at this mixture here.
Bromine vapor is more dense than air and can be poured. When the bromine enters the flask, it mixes with the air already present.
There are a couple of things with this mixture here. One is some of the bromine in the air must have escaped here, because when we look at the gas here, there are 3 particles here. When we look at the gas here, there are 6 particles. Now, when the particles collide with the wall, it generates an impact, and that impact is felt as pressure. And so actually this has double the pressure here than this. This is why there's a sealed lid here. This was an open lid. And so what has to happen is, in order to maintain the same pressure, you know, if we generate a high pressure here, that's going to push the lid up. And so in order to maintain the same pressure, some of the air must have leaked out of here, you know, and some of the bromine must have leaked out of here. Otherwise, it's going to be higher pressure in there. As far as pressure goes, gases are pretty interesting in that it exerts pressure evenly. This is for small samples. You know, for small samples, the pressure at the top is the same as the pressure at the bottom. However, for large samples, let's say we're looking at a gas, a very large sample. Let's say we're looking at the atmosphere. If we're looking at the atmosphere, oops, it's not working. Then the pressure is different. You know, when you're looking at the atmosphere, the pressure is heavier at the bottom. Let's say this is Mount Everest here. When you go to Mount Everest, the air thins out here. And so for people at sea level, let's say you're at sea level down here, the pressure is going to be higher at the bottom than at the top. If you're at the top of Mount Everest, the pressure is about 1/3. And so if you had a gigantic sample of gas like this, and then put a pressure gauge down here at sea level and a pressure gauge up here, you know, above Mount Everest, then there's definitely a difference in pressure. The pressure at the top is going to be less. But this is a lab size sample, or a room size sample, or a building size sample. If we have a building size sample like 10 stories, the pressure barely changes. You know, we need much larger. However, liquids, we're going to have much higher pressure at the bottom than at the top, you know. And in other words, the liquid's going to weigh much more down here than up here. And so the gases, they exert even pressures because these are just moving in random lines, and they collide with the walls. And they collide with the walls, generating the pressure, you know. And these are just moving in random directions. Over here, you know, these are stuck together, and so it's going to weigh more down here than at the top. Everything's all connected. And then again, pressure is the force of these collisions over unit area. So, you know, we have things bouncing down here versus bouncing up here. And so you can look at the pressure gauge. The pressure gauge is maxed out here, but it's reading 0 here. Let's call that 0 at the top, and then it's maxed out down here. Whereas the pressure gauge here in the gas is totally even, you can see. As well. On to the next one. So when we try to visualize the gas at a particular level, we use kinetic molecular theory. Kinetic is motion and motion of molecules. And so these are the basic constructs of this. But this is kinetic molecular theory for what's called an ideal gas. We'll talk about ideal gases and real gases as well. But for an ideal gas, Okay, well, ideal versus what? Versus a real gas. And so we'll talk about the difference between an ideal gas and a real gas later in part 2. For right now, these are the basic concepts behind kinetic molecular theory for an ideal gas. 1, a gas consists of molecules and empty space. Okay. 2, the volume occupied by the molecules in a gas is negligible when compared to the volume of the space they occupy. So it's practically all empty space. And let's say if I had 1 liter of helium, it's almost 1 liter of empty space because the helium atoms barely occupy any of that space. 3, the attractive forces among molecules of a gas are negligible. Okay, this is what makes it ideal. You know, if the attractive forces are negligible or 0, that's it. 4, the average kinetic, this also makes it ideal, you know, is negligible. That's ideal. Sometimes it's not negligible. Sometimes it's significant. When it's significant, then we're dealing with real, when this is not negligible anymore. And when this is not negligible anymore, then we have to deal with real. 4, the average kinetic energy of a gas molecule is proportional to temperature. So temperature and average kinetic energy are kind of two of the same thing, expressed in kelvins. Kelvins, the temperature we use. Molecules interact with one another and with the container walls without loss of total kinetic energy. And so what this says is there are two types of collisions. There's something called an elastic collision versus an inelastic collision. An elastic collision is like two pool balls, pool, like they bounce off each other quite nicely. But inelastic collisions would be like two soft, wet clay balls. Clay is just going to kind of stick and deform and stick together. So if you had two soft clay balls colliding, then they're probably going to get stuck together and not bounce off each other. And so when we visualize these collisions happening between the molecules in a gas or the atoms in a gas or whatever you have in the gas particles in a gas, they bounce off each other and they'll get stuck. However, sometimes they do get stuck. Sometimes they act like two soft, wet clay balls. And that's when the attractive forces are strong and non-negligible. If the attractive forces are strong, they want to stick together if they come into contact. They don't want to bounce off each other. So let's connect molecular theory. Let's go on here. Next slide here. So it's mostly empty space. So this is an illustration showing it. In a liquid, there's very little empty space because all the water molecules are touching. So this is 100 samples of so they'll just take 100 snapshots of this. If they take 100 snapshots of this, once in a while we'll see a molecule. Most of the time it's empty. And so this is it. That's an illustration. Another way of thinking about this is to think in terms of the mean free path and the collision frequency. The mean free path is the average or the mean length or distance a molecule can travel before it hits something. And so at around ambient pressure, a particle can travel 68 nanometers. A nanometer is, 1/1 billionth of a meter. And so it travels 68 nanometers before it hits something, like a wall or another molecule, at ambient pressure. At extremely high vacuum, that molecule travels 100,000 kilometers before hitting another molecule. And so it's totally empty. And so a huge difference. This is extremely high. We don't have extremely high vacuum on Earth. It's too high. We have ultra high vacuum on Earth. This is too hard to achieve because of things called vacuum leaks. But we could get ultra high vacuum. If you have ultra high vacuum, then the particle can travel about 1 kilometer before hitting something, so it just travels, and hits something. And so comparison between ultra high vacuum and ambient pressure, there's a huge difference. Mean free path and ambient pressure is 68 nanometers. That's not very far until it hits something. It is pretty far in terms of, because an atom or a particle is around the picometer or hundreds of picometers. And so atom is many, many orders of magnitude smaller than a nanometer. A nanometer is actually a long distance compared to the size of the atom. And so even though this is such a tiny distance, an atom is, how big is an atom roughly? Let's see. So an atom is, let's say, about 100 picometers on a small atom. So big atom is about 600 picometers. So let's say an atom is about 100 picometers roughly, 100 picometers. Pico is 10 to the minus 12 meters, right? And then this is nanometers. The mean free path is a nanometer. And so let's say 68 nanometers, 68 nanometers. A nano is 10 to the minus 9. So it's about 1,000 times the size of this, you know, that it can travel. So this is not, if let's say the atom's this big, so it'd be about 1,000 times. So I got to make it a little longer than that. So put 1,000 of these, line them up roughly, and then it will collide with another atom over here, get some kind of collision, boom. In that. And so, you know, even though it doesn't seem very long, compared to the size of an atom, it's kind of long. And so even at ambient pressure, we say gas is mostly empty space. And so this is ambient pressure here. So this is saying that, you know, the next molecule is about 1,000 times its size away, you know, that kind of thing. So mostly empty space. You don't need to memorize these numbers. These numbers are just to give you some perspective on this type of stuff. This is number density, how many molecules per cubic centimeter, pressure, etc. Temperature, in terms of kinetic molecular theory, temperature is related to motion. Higher the temperature, the more motion we see. So let's take a look. What's this illustrating here?
If the temperature of a constant volume of gas is increased, the molecules of the gas move faster, and each collision exerts a greater force on the walls of the container. In addition, because the molecules move faster, the number of collisions between gas molecules and the container walls increases, and therefore, so does gas pressure.
So the higher the temperature, the greater the pressure. One, more collisions per second. That's called collision frequency. And two, more violent collisions because they're moving faster. And so higher temperature, we're going to come back to that later. And so how do we measure pressure? When we measure gas pressure, it depends on if we're trying to measure the atmospheric pressure. This is the atmospheric. And atmospheric pressure varies. You know, there's low pressure regions, high pressure regions. You know. And this is, who's this? This is Torricelli. Torricelli, the inventor of the mercury barometer. Yeah. Torricelli is known for the statement, "We live submerged at the bottom of an ocean of air." You know, and so at the bottom of the ocean of air is going to be the heaviest. You know, as we go up higher, it's going to be lighter. Weight and pressure are kind of the same thing. You know. And so how does a barometer work? A barometer works like this. Inside this is closed. This is like an inverted test tube kind of deal here. And up here is a vacuum. A vacuum means it's empty. There's nothing in there. It's not a perfect vacuum. And that's what it is. And so what we have is we have the weight of the atmosphere. This is like a triple beam balance in the sense that, in this sense, let me just show you here. This is like a triple beam balance because on the one hand, oops, working. On the one hand, we have this stuff on this side of the balance. And on the other hand, we have this stuff on the other side of the balance here. And so this is like a seesaw. And so some person sitting on this end of the seesaw, another person sitting on the opposite end of the seesaw. And when these two weights are the same, then we've reached the state where it's stable here. In other words, the two weights are equal. And so what's weighing on the outside? Well, this is just an open pool of mercury. And so what's weighing on the outside is the weight of the atmosphere. So we have the atmosphere here, it's pushing down on this pool of mercury here. What's pushing down on the opposite end? What's pushing down on the opposite end is we don't have any gas here. So in this vacuum, there's no gas. And so we have no weight of the gas. The only thing that's pushing down on this end, on this side here, is the weight of the mercury. And so over here is the weight of the mercury. So if the weight of the atmosphere is equal to the weight of the mercury, then this is stable. And so, in other words, if we're at the equator down here on an average day, then the atmospheric pressure on an average day is 14.7 pounds per square inch. And so if I take a square inch of this, there's 14.7 pounds sitting on that. Well, that must mean that this column mercury must weigh 14.7 pounds as well per square inch. Well, 14.7 pounds of mercury per square inch means I have to fill it up with a lot of mercury. Well, how much mercury do I have to fill it up? Well, I'm going to have to fill it up to a height of 760 millimeters. If I can fill it up to that height, then I get 14.7 pounds of mercury per square inch. If I go higher, you know, then I'll have more pounds. If I go lower, I'll have fewer pounds. You know? But on an average day, it's 14.70 pounds. And so this is what we call atmospheric pressure, or standard atmospheric pressure. Okay. Well, we don't want to weigh the mercury. And so what we do is we just measure the height of the mercury column. And so even though height or length of mercury column is not pressure, it's related to how much mercury we have, which is related to how much it weighs, which is related to the pressure. And so this is a weird unit because it's not a typical pressure unit. And so it turns out that 760 millimeters of mercury liquid is equivalent to 14.70 pounds per square inch. Well, that's normal pressure. And so we call that 1 atmosphere of pressure, ATM. ATM stands for atmosphere pressure. And so that's 1 atmosphere. Clear this. So as atmospheric pressure changes due to the winds and the weather, you know, we could have less weight on the outside or more weight. You know, less weight, this drops. More weight, this gets pushed up like a seesaw. And so our standard unit is atmospheres here. Oops. Do that again. Our standard unit of pressure is the atmosphere. It might be changing. It's abbreviated ATM. This definition I'll talk about in a second. It's related to millimeters of mercury, you know, how high it goes, or inches of mercury. You know, if you want to convert millimeters to centimeters and then centimeters to inches, we can do that. And so you'll often hear inches of mercury if they want to use English units versus metric units here. That's 760. So 1 atmosphere is 760 millimeters of mercury. In honor of Torricelli, the inventor of the barometer, they also call 760 millimeters torr. And so rather than using millimeters of mercury is nice because you can visually see that versus torr. But a torr and a millimeter of mercury are the same thing, so 760 torr. Pascal is what's used in Europe quite a lot and other metric countries. A Pascal has a different definition. This is just your average pressure on a nice sunny day. A Pascal is based on physics, you know, how many newtons of force per meter squared, etc. And so this has a physics definition. And so it turns out, if we look at it, a Pascal, and compare it to an atmosphere, there are 101,325 pascals per atmosphere. And so this is why it's saying by definition here. This is by definition here. That's what they did. But it's by definition based on this physics interpretation. But 101,325 is a hassle. And so we like to use kilopascals. It'd be 101.325 kilopascals. But that's still kind of a hassle. And so we can use bars instead. A bar is 10 to the 5th pascals. And so we can move the decimal 5 places rather than 3, and we get 1.01325 bar. And so a bar is very common in other countries. An atmosphere is common in the US, you know, but they're very close. 1 atmosphere is equal to 1.01325 bar exactly. And so typically what we just say is 1 atmosphere is about equal to 1.01 bar if we do it to 3 sig figs. Okay, so an atmosphere and a bar are about the same. It's only off by 1%, which is not huge. Inches, we just convert millimeters to inches. So 760 millimeters gives you 76 centimeters. 76 centimeters is about 30 inches. And so 29.92 inches of mercury is the standard pressure. And then we have PSI, pounds per square inch. And it's 14.70 to 4 sig figs pounds per square inch of pressure. Okay, weight and pressure are the same thing. These you don't have to memorize. These. The only one you have to memorize is this. Atmospheres to millimeters mercury in torr. What if we don't want to weigh the atmosphere? Barometers are used to weigh the atmosphere. If we have a gas sample, like in this Erlenmeyer, this is called an Erlenmeyer flask, has this conical shape. If we wanted to measure the pressure inside this flask, I don't want to put a miniaturized barometer in here. In fact, they don't make barometers small enough to put inside here. In order to weigh the gas in here, we'd have to put a very, very tiny barometer in there. Well, the barometers are huge, you know, and therefore we can't. In fact, do you know why they pick mercury for barometers? You can make barometers out of anything. So the reason they pick mercury, let me just go back to this slide here for a second. The reason they pick mercury is because mercury is so dense. What is the density of mercury? The density of mercury is about 13.6 grams. So it's about, oh, is it 13.6? Can't even remember. Let's see. So we, 76 centimeters of mercury, which is 760 millimeters, which is about 3/4 meter. Mercury has a weird shape, meniscus. Do you see the mercury meniscus is convex? That's because mercury doesn't like to touch glass, whereas water loves glass. Water tries to climb up the walls of the glass tube, so it's concave. That's it. So anyway, going back to this, we could use any one. So 14.7 pounds of mercury is 760 millimeters, or about 3/4 of. Do you know what 14.7 pounds of water per square inch is? If we use water instead of mercury, then we'd need about 30 feet, if we use water. Because water's a lot less dense. And so 14.7 pounds of water goes up 30 feet, whereas mercury is about 13 times more dense. So that only goes about 1 meter up for mercury. And so water, we could use other liquids too, but the most dense liquid is mercury. And therefore they use mercury in this. And mercury is not healthy, but it's practical. Other liquids aren't practical because they're so light compared to mercury. And in that case, if it's too light, this tube is going to extend sky high. Okay, let's go on here. All right, now let's measure the pressure. We can't miniaturize a barometer. If we could just place it inside the flask with the barometer. And so instead we do this. This is going to be a seesaw here, like this. On one end sits this. On the other end sits this. And so we have to look at what's sitting on each end of the seesaw. On the left end here, we just have the gas, this yellow gas. So this yellow gas is exerting a weight here on this end. On this end, we have two things. We have the weight of the mercury here. So we have the liquid mercury, which is going to weigh some amount. And then we have the weight of the atmosphere, because this is open-ended. This has an opening here, and so the atmosphere can come in here. You know, it's open to the air. And so we have the weight of the atmosphere here, plus the weight of the liquid mercury. This is like if you go swimming in a swimming pool. You know, let me show you what happens, let's say, or the ocean. Oops. Let's say this is a very deep pool. Let's say this pool is about 30 feet deep. If you're sitting on the top here, on the side of the pool, then you have the weight of the atmosphere. And we call it P atmosphere, or we call it PBAR. BAR stands for barometric pressure. And we're just going to say it's 1 atmosphere here. So we got the weight of the air on there, 14.7 pounds. And then we go swimming here. And so if we go swimming, well, not only do you have the weight of the atmosphere on top of the pool, but you're also going to have the weight of the water on top of you. So you're going to have two. You're going to have the weight of the H2O liquid water on top of you here. And so what is that? Well, we could figure it out using some physics here. But let me just do the calculation here. I think it's 13.6 was the density. 13.6 times 760 is 10,336 millimeters divided by 1,000 is 10.3 meters. So we got to go down 10 meters. Well, 10 meters is approximately 30 feet. And so if we have 1 atmosphere of pressure here, and then we go 30 feet down, that's about 14.7 pounds of water on top of you. And so the pressure of the water is going to be 1 atmosphere. So if you're down about 30 feet underwater, you're going to experience a total of 2 atmospheres. 1 atmosphere of air plus 1 atmosphere of water. So you're at about 2 atmospheres of total pressure here, down here. So this is kind of the same thing. You're under a pool of mercury. Not only do you have all the weight of the air on top of you, but you also have the weight of all this mercury on top of you. So if you're swimming down here, although you wouldn't be able to sink under mercury because it's so dense, but if you're swimming down here, you'd have both of these weights on top of you here. I'll give you. And so what that means is this, the 2 weights are equal here. So it means that the pressure of the gas inside this flask is equal to the pressure of the atmosphere plus the pressure of the liquid mercury. Well, conveniently, the pressure of the atmosphere is measured using the barometer. So we have millimeters of mercury. And then here, we could just measure how many millimeters of mercury we have from here to here. And we're going to just use the height here, the millimeters of mercury. That would be the pressure of the mercury here. And so this is also going to be millimeters of mercury. And so we just have to, go to the barometer and measure the atmospheric pressure or the barometric pressure, and then just measure how tall this is. That's it. This is kind of the opposite scenario here. This is a case where the gas weighs less than the atmosphere. The atmosphere weighs more. So we got 14.7 pounds or so from the atmosphere here pushing down. This is open tube. And then on the left, we got the weight of the gas. the pressure of the gas, plus the pressure of this mercury column, pressure, which is here, P mercury. And so the pressure of the gas plus the pressure of the mercury is equal to the pressure of the atmosphere. Therefore, the pressure of the gas is equal to the pressure of the atmosphere minus the pressure of the mercury here. Okay. What happens if the two levels are equal? And so let's take a look at that scenario here. And so another scenario is if the two levels are equal. And so we might have the Erlenmeyer flask. This is cone-shaped flask here. This is called a U-tube or a manometer. So I better write that down. Let's say the two levels are equal. Then what's pushing down on the left is the pressure of the gas. What's pushing down on the right is the pressure of the atmosphere. So in this case, the pressure of the gas is equal to the pressure of the atmosphere, because both are weighing the same amount here. And so this is called the open-ended or open-ended manometer. A manometer is used to measure gas sample pressures. Manometer here. So let's take a look at this here. Which one weighs more? The atmosphere, which is this open-ended? Oh shoot, is that open or closed? This looks like a closed-ended monitor. This is open-ended. Why would they do that? I never looked at the drawing this blown up. But we're going to call it an open-ended manometer. So this is open. If it's open, then we have the weight of the atmosphere here, or the pressure of the atmosphere. And here we have the pressure of the gas. Which one weighs more, the atmosphere or the gas? Let's see, got to do this. Yeah, good. The gas weighs more, a lot more. Oh, sorry, I missed the chat. Can you explain 2 and 3 again? I will. We're going to do these examples here. Okay, yeah, the gas. This seesaw is like this. You know, the gas weighs a lot more, so the atmosphere gets pushed up here, and the gas is pushed down here. So what we need to do is we need to add some weight to the left side. The way we can add the weight to the left side is by including the liquid mercury. And so we'll do that like this here. Like that. Okay, now when we do that, we take a look at this. Now it's balanced, yeah, but we have to add this bit of mercury here. The pressure of the mercury. And so if I take the pressure of the atmosphere plus the pressure of the mercury, that's going to equal the pressure of the gas. And so the pressure of the atmosphere plus the pressure of the mercury is equal to the pressure of the gas. Okay, the pressure of the atmosphere I get from the barometer. The pressure of the mercury I get just by measuring the height. In this case, it's 173 millimeters of Hg. Let's say the barometric pressure today was 760 millimeters of Hg, normal. And so the pressure of the gas must be 1033. So it looks like the pressure of the gas is equal to 1033 millimeters of mercury. You know, if the barometric pressure was 760. Barometric pressure fluctuates a little bit, you know, day to day. Okay, any questions on that? Okay, let's go on to this next one. All right, here, which weighs more? Again, this is closed-ended. It's not supposed to be closed-ended because this book doesn't talk about closed-ended manometers. Closed-ended manometers, there's no weight of the atmosphere. Closed-ended manometers, this is a vacuum here. And since it's a vacuum, we don't have to worry about the weight of the atmosphere because the atmosphere can't get in there to weigh it down. And so closed-ended manometers aren't talked about in this book. So I'm going to open the end of this manometer here. 760 is normal, yeah. And so let's make that open. And so now the atmosphere can weigh in here. So in this case, what weighs more, the atmosphere or the gas? Yeah, you're right. And so in this particular case, the atmosphere weighs a lot more than the gas. The gas is over here. And so you can see the seesaw is totally unbalanced. So what we try to do is make the seesaw level by adding some more weight to this side. Well, we have to add this much, the weight of this much liquid mercury, 284 millimeters liquid mercury here. And so what we get here is the pressure of the atmosphere is equal to the pressure of the gas plus the pressure of the liquid mercury. All right. So again, we're going to just go to the barometer and measure it. Let's say in this case, the barometric pressure was a little lower. Let's say it was 758 millimeters rather than 768 millimeters mercury. I mean 760. 760 is normal, so it's just slightly less than normal. And then this is equal to the pressure of the gas, and then the pressure of the liquid mercury is just how tall it is, 284 millimeters mercury, 284 millimeters of Hg, and therefore the pressure of the gas is equal to, in this case, 758 minus 284, and that's going to give us 474 millimeters of mercury in here. So the gas here doesn't weigh that much, 474 millimeters of mercury. Okay. This is what we call absolute pressure. I wrote it here, but I didn't talk about it. This is absolute pressure. Absolute pressure versus gauge pressure. So let's talk about that right now. When we're dealing with absolute pressure, let's see this. If we have zero pressure, it's empty. There's no gas in there. No gas. And so there's nothing in there to cause collisions. This is empty. Therefore, no collisions. No collisions. However, when we're dealing with gauge, and we see we have zero pressure on the gauge, it's not empty. When we have zero pressure on the gauge, it just means that this. Okay, let's go to helium tank. Let's say you're filling balloons. Helium tank. So there's helium atoms in there. Helium tank. And then we have helium inside here, helium gas. In order for the helium gas to come out of the tank, we need a higher pressure. So when we look at the gauge here, let's say the gauge is at 30 psi. To make a distinction between this, we use PSIA here for absolute, or we use PSIG for gauge. So let's say on the pressure gauge, it's reading 30 psi and we can fill up our balloons. Eventually the gauge is going to get to 0 psi. When the gauge gets to 0 psi, then we aren't going to be filling up any more balloons. We say that the tank is empty. And so this is going to be gauge. So I'm going to add a G and a G here. We say it's empty, but is it really empty? It turns out it's not empty. There's still a little bit of helium left in here, like that. There's some residual helium left in there because what we need is we need a pressure difference. Here. And so when we look at the air, there's going to be air outside here, like this. And the air pressure out here, that is the P atmosphere, is going to be lower than the pressure inside here, so the helium can escape. But when this tank goes empty, then what happens is that the helium pressure inside here is equal to the atmospheric pressure outside here. If this tank were truly empty, then the air would be sucked back in here. Because if this tank were truly empty, we would have a vacuum. And so to have a truly empty tank, this has got to be a vacuum which sucks in all the air back into the tank. And so what's going to happen is eventually this is going to go empty because the helium isn't forced out. In other words, if we have one atmosphere outside here, and we have one atmosphere inside here, then it's balanced. You know, we need a pressure differential. In other words, if we have 14.7 psi out here, then we are going to have 14.7 psi inside here. And that's what we call empty, you know. So we have different things. So when it's reading PSIG, it's not really empty. And so let's take a look at the gauge in a little bit more detail here and compare it to atmospheric. So if the gauge is reading 0 PSIG, then let's go to maybe, let's go to 14.7 PSIG here. Okay. And so this is 14.7 PSIG, and then we let the gauge go to 0. Then the tank is empty. But it's not truly empty. It's just not being forced out. If we need to get the rest of this helium out of here, we have to hook up a vacuum to this. If we hook up a vacuum to this and suck it out, we're going to have this. We're going to get to negative 14.7 psig. And so negative 14.7, that's vacuum. Yeah, 14.7 is an important number because 14.7 is normal pressure, atmospheric pressure, 14.70 here. And so in order to suck the rest of this out, we got to suck out all 14.7 psi out of there, creating empty, truly empty vacuum. Okay, that's psig. Okay, well, what I'm going to do is I'm going to put an overlay psia on top of that here. And so at minus 14.7 psig, that's actually zero psia. So that's truly, there's no gas there. 14.7. This is what we call vacuum. And then over here at 0 psig, this would be 14.7 psia. And over here, this would be 29.4 psia. So it turns out that the gauge 0 psig is equal to the atmospheric pressure. Absolute. So you might have an empty tire, but the empty tire is filled with just 1 atmosphere of air. That's considered empty. To make a truly empty tire, you have to suck out all the air that remains in there and create a vacuum. We'll do a problem with this. Illustrate it. All right. Well, let's take a short break here. Let's take like a 5-minute break and then come back. 5 minutes. Okay. Think about this. If you have any questions. Okay, we'll get started again here. We're almost done for today, but we have to, whenever we're dealing with gauge pressure, we have to correct it because zero is not really zero pressure. Zero is just atmospheric pressure. It feels like we're under zero pressure right now, and so it's just an arbitrary zero, not in the vacuum of space. Okay, continue on here. Okay, what we're going to do is we're going to look at some simple laws. And the laws, these are going to be derived empirically. So we take some data, so they take some observations here. And so they're measuring the pressure based on the height of the mercury versus temperature. No, actually volume. This is not height. This is height in terms of the volume. So this is very tricky. They're looking at the height. I guess the bigger the height, the bigger the volume. So we were just talking about height in terms of millimeters of mercury. They're talking about height in terms of volume here. And so whichever. In other words, I guess the higher the height, oh, here it is, the height of this gas here, plug goes up, the greater the volume. And so what they're saying is the gas expands with temperature here. It looks like it's linear. So they took 4 data points here. It's linear, and then they can draw a line. Since we can draw a line like this, we can come up with an equation. And the equation of the line is an empirical equation. And what is it going to look like? Well, it's going to be the volume here. So the y is equal to mx plus b. So y is the volume, m is the slope, x is the temperature, and b is the intercept. And so when we look at the intercept here, this is the intercept. It depends on what unit we use. If we use Kelvin versus Celsius, if we use Celsius, the intercept here is minus 273. If we use Kelvin, the intercept is 0. And so it depends on if we're using Celsius. If it's Celsius, it's minus 273 degrees Celsius. If it's Kelvin, it's plus 0 Kelvin. So to make a long story short, this is more of it, and this is more of a particulate picture of this, is this. The volume is equal to m times T if we use absolute temperature. And if that's the case, then volume is directly proportional to the temperature. So if I double the temperature, I double the volume, etc. In other words, if we do it like this, from this equation, we can get volume over temperature is equal to m, which is a constant, the slope. And the proper form of Charles' law is in the more usable mathematical equation than this. And that is V1 over T1 is equal to V2 over T2. So if I change the temperature, the volume has to change proportionally, or if I change the volume, the temperature has to change proportionally. So this is the proper form of Charles' law that we often use here. And it just comes, these mathematical relationships, these empirical relationships here. We're going to look at that more. Here's a demo of Charles' law. Let's take a look at that. And so here's a balloon, and this is liquid nitrogen here. So the balloon's being cooled. So the gas, this is air in the balloon. And the air is being cooled by the liquid nitrogen. Liquid nitrogen is very cold. And the gas is contracting because of the temperature. It's getting colder and colder, and volume contracts. If you want the audio, go to physics demo, but this was a 5-minute video, so it's too long. And then they allow it to warm back up to room temperature. You allow it to warm back up to room temperature, the gas expands. Keep an eye on that balloon, it's gonna expand. This balloon's air, this balloon here is helium. So helium is gonna do the same thing essentially. So I cut the video off there. This is Boyle's law. Boyle's law deals with volume and pressure. So we take some observations and we look. This is nonlinear here. Do you see the curve? It's curved. And so we can't come up with a simple equation like that. Yeah, that's right. Karin and Diana, basically Karin. That's fine for Boyle's law. I mean, Charles' law is like that, volume and temperature. Boyle's law is a little different, here. It's going to be inversely proportional. And so when we look at the volume here and we come up with a mathematical relationship, which I'm kind of skipping here, coming up, but the volume is inversely proportional to the pressure. So if I increase the pressure, I actually decrease the volume. If I decrease the pressure, I actually increase the volume. And so it's inversely proportional. And that's what this curve shows us here. And you can see it kind of here, but I'm not going to talk much about this. And so we can come up with another relationship here. What can we come up with? We can come up with this relationship. Actually this is equal to constant up here. And so what we can say is P1 V1, so we'll just multiply both sides by P, is equal to P2 V2, which is equal to a constant, which is the slope. It's not really slope because this is nonlinear, so it's not the normal way we think about it, but it gives us a different relationship. And so this relationship is called Boyle's law. This is Boyle here. It's curved, right? It's nonlinear. This is nonlinear. We haven't talked about nonlinear, the math involved there, but we do the same thing. If it's linear, we have y equals mx plus b. If it's nonlinear, we have other equations for that here. It's Boyle's law. We'll look at some applications of Boyle's law and Charles' law in a minute. But really, I don't care if you know Boyle's law or Charles' law. It's nice to respect those historic figures, but you can forget about Boyle's law and you can forget about Charles' law because all we need is the combined gas law. And so I'm not going to worry about Boyle's or Charles. And in fact, I'm going to do the complete combined gas law. The complete combined gas law looks like this. It's going to be P1 V1 over T1 is equal to P2 V2 over T2. This is the Chem 4 version here. If you go to Chem 1A, the Chem 1A version is going to look like this. P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. This is where N is the amount of gas, amount in moles of gas. I forgot, I thought I put the other video. The more moles of gas you have in there, the higher the pressure is going to be. I had another video, I forgot to load it on here, but it's on the website also. And so the number of moles, this is, we use this equation, the Chem 4 version, if we do not add or remove gas. No gas is added or removed. We use this version here if we're going to, bleed out some gas or force some more gas in. We change the amount of gas in this. The amount of gas doesn't stay. The only thing that changes is the pressure, the volume, and the temperature of that particular gas. Okay, so let's take a look at some calculations involving this now. Logged out of here. Yep. Try to log back in. All right, chapter 4, introduction to gases. I'm going to go to the end here. All right, so let's do the same thing. We'll get a start here and then see what properties of gases are the result of kinetic character of gases. Well, pressure is, especially pressure from the collisions. Temperature is, volume, I think all of them. All gas properties relate, yeah. Pressure, volume, and temperature. State how and explain why the pressure exerted by gas is different from the pressure exerted by solid or liquid. You know, solids or liquids, let's just see what they said. Oh, it's still on the slideshow? Sorry, thanks. Okay, can you guys see? Yeah, okay, great. Okay, so we looked at what properties of gases are a result of kinetic molecular theory, all the properties, basically. State how and explain why the pressure exerted by gas is different than the pressure exerted by a solid or liquid. Gas molecules move independently of one another in all directions. Therefore, they exert pressure on the container walls, including the top, uniformly in all directions. Liquid and solid particles are a result of gravity, so they exert a downward pressure on the bottom of the container. Liquid particles can move amongst themselves, so they exert horizontal pressure against the walls of their container. Solid particles lack this freedom of horizontal movement, so they exert no horizontal pressure on the walls, just vertical pressure on the floor. What are the desirable properties of air in an air mattress used by a camper? Show which part of kinetic molecular theory is related to each property. I don't know, spongy? We'll just read. You read it here. And so we go through and do this. Just as quick. So I would do the same thing. We don't have enough time to do the same thing for chapter 4. And so let's take a look at some of the calculations that we're going to do in chapter 4. So these are typical problems that we use the combined gas law. The pressure of 648 milliliters of gas. Okay. And so I would write it like this. I'm going to call this V1 here. Is changed from 772 torr, so I'm going to call this P1, to 695 torr. I'm going to call this P2. What is the new volume? So we'll call that V2. And so I only use one equation, P1 V1 over T1 is equal to P2 V2 over T2. Now, did the temperature change? They said they didn't mention anything about a temperature change. So if the temperature doesn't change, then it cancels out. And we're left with P1 V1 is equal to P2 V2. And then let's solve for V2. V2 is equal to P1 over P2 times V1. And then let's just plug it in. P1, we don't have to change the units here. The units just have to be the same. So 772 torr. P2 is 695 torr. V1 is 648 milliliters. 648 milliliters. And let's see what we get. And so we can see what we get here. Let's just see if I set it up correctly. Yep, set up. Comes out to 720 milliliters. Thing is, they might have rounded this off, so I'd like to know the number before they rounded it off. Here. A cylindrical gas sample has a piston at one end that can be used to compress or expand the gas. If the gas is initially at 1.22 atmospheres, so 1.22 atmospheres, that's going to be our P1. The volume is 7.26 liters, that's our V1. What will the pressure be? So this is our P2. If the volume is adjusted to 3.60 liters, so this is V2. So this is the same kind of deal. We're solving for P2 using the same equation above. So P2 is V1 over V2 times P1. and just plug in and plug it in and see. And so let's see what they got. So here's our P1, 1.2 atmospheres, and then our V1 over V2 here. Pressure goes up. The volume gets cut in half, the pressure pretty much doubles. The volume got cut in half, the pressure pretty much doubles. Let's see some other problems here. So this is a series of combined problems here. Let's take a look at 41 here. 7.717 liters. So we'll just call that V1. Exerts 744 torr. So we'll call that P1. At 27 degrees C, we'll go this T1. Now there's a problem. The problem is this. If you look at Charles' law, volume is MT plus, we have two intercepts. One is if the temperature is in Celsius. If the temperature is in degrees C, then the intercept is plus or minus 273 degrees C. Or if it's in Kelvin, so volume is equal to MT. If this is in Kelvin, then the intercept is 0. So this is just volume is proportional to temperature. So unless we want to use this offset, unless the offset means more algebra, we could use Celsius, but we have to offset it. We might as well do this. We might as well, the first thing we got to do is we got to go to Kelvin, otherwise it doesn't quite work. So we do 27 plus 273 Kelvin, which gives us 300 Kelvin. And so this will be our T1. Otherwise I have to deal with this. I don't want to deal with that. Adding 273 or subtracting 273. I don't want to deal with that. And so I'll just convert the temperature to Kelvin so I don't have to deal with the intercept here. Okay, and then suddenly compresses the gas to 48.6 atmospheres. So this is P2. Temperature goes to 547 degrees C. This is T2. What is the final volume? This is V2. And so T2, I need to convert that to Kelvin too. So that's 547 plus 273. So that's 10, 12, 820 Kelvin. And so that's our T2. And so we just saw it's P1 V1 over T1 is equal to P2 V2 over T2. And we're solving for V2. So V2 is equal to P1 over P2. And then T2 over T1 times V1. And then just plug in the numbers and see. So let's see what they did here. And basically that's what they have here, except they dealt with this kind of thing where they corrected it here as they went along. So I wouldn't have to do it in the equation here. Okay, this is what it's going to look like. The combined gas law, let's do that. Combined gas law is a combination of Charles, Boyle's, and another guy's law. The combined gas law in Kelvin looks like this. P1 V1 over T1 is equal to P2 V2 over T2. If we use degrees Celsius, then it looks different. It's going to be P1 V1 over T1. We got to convert Celsius, so plus 273 degrees is equal to P2 V2 over T2 plus 273. So we have to factor in the offset here. So I don't want to memorize different equations. I just want to memorize one equation and make sure the temperature is in Kelvin. That's it. And so that's why I converted to Kelvin before. As otherwise I have to memorize the equation for Kelvin, and I have to memorize the equation for degrees C. Well, I don't want to do that. I'll just make sure I convert the temperatures to Kelvin, and then I can use this. Okay. That's why. Why have the arbitrary conditions of STP been established? Oops, I forgot to talk about STP. I didn't even have that in my slide. Do you know what STP stands for? We'll talk about that now. STP stands for standard temperature and pressure. I don't like STP. This is personal bias. Some people want to know the STP volume. What's the STP volume of helium? What's the STP volume of this gas or that gas? Standard temperature, this is the reason I don't like it. Standard temperature is 0 degrees C. Standard pressure is 1 atmosphere or 1 bar. It's 1 atmosphere if you're in the US, or it's 1 bar if you're in Canada or Europe or wherever. They'll use bar. So I don't know what, I'm not sure what Mexico uses, bar or atmosphere, but this is it. Now, the problem that I have with standard temperature is it's at 0 degrees C. This is fine, the pressure is fine, either bars or atmosphere, that's fine. But 0 degrees C, who works inside a 0 degrees C lab? And so I don't really like it. I'd like room temperature. But let's see what they say. They say STP conditions have been established so that all data are reported in the same conditions. 1 bar pressure, oh, they're using 1 bar, is easily achieved in laboratory, but 0 degrees C is not a convenient temperature. So it's just a reference point. If they picked a reference point, I wish they would have picked room temperature instead, because it would give you a more meaningful number. If 1 cubic foot, 28.3 liters of air at common room conditions of 23 degrees C and 0.985 bar is adjusted to STP, what does the volume become? In fact, you know, I'm going to skip most of these STP. STP is just, you know, setting it to 273 Kelvin and 1 bar. I might do 1 STP calculation, but that's about it. Let's look at the more challenging. We don't have much time left, so we'll take a look at more challenging problems here. Very small dust particles seen in a beam of light passing through a darkened room appear to move erratically. That's kinetic molecular theory. The molecules are colliding with the dust, causing them to be pushed around. Molecules you can't see, so there's invisible collisions there. The volume of the air chamber of a bicycle pump is 0.26 liters. The volume of a bicycle tire, including the hose between the pump and the tire, is 1.80 liters. If both the tire and the air in the pump chamber begin at 743 torr, what will the pressure in the tire be after a single stroke of the pump? Well, that's what helps in a lot of these problems is to try to draw this pictorially. And so let's end with this particular problem here, and that is we'll have the pump. We'll have a pump here, bike pump, and then there's going to be a tube to a tire, bike tire. So the bike pump is 0.26 liters, and the tire is 1.80 liters, including this hose. And so we see the total volume here. The total volume is 2.06 liters. That's V initial, or V1. That's our initial volume. And then they push the pump in. If they push the pump in, then we're going to lose 0.26 liters. So if they push the pump in, then V2 is going to be 1.80 liters. And so 1.80 liters is V2 because they push this pump in and force the air inside here. So that's V2. Okay, if both the tire and the air in the pump chamber begin at 743 torr, so this is going to be 743 torr. So that's my torr is pressure, so that's my P1. Then what is P2? Okay, so we use the combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. Now the temperature, they don't say anything about the temperature, so we assume that the temperature didn't change. And so that cancels out. So we're left with this. So we're solving for P2. P2 is equal to V1 over V2 times P1. And so that should give it to us. So let's see if they did here. Yeah. So here's V1. It's 2.06 liters. Here's V2, 1.80 liters. Here's P1. So I went up to 850 torr. Let's see, do we have time? A hydrogen cylinder holds gas at 3.67 atmospheres in a laboratory where the temperature is 25 degrees C. To what quantity will the pressure change when the cylinder is placed in a storeroom where the temperature drops to 7 degrees C? And so again, here. So P1 V1 over T1 is equal to P2 V2 over T2. So we'll call 3.67 atmospheres P1. 25 degrees C is T1 in Celsius. We need to change that. That would be 298 Kelvin in Kelvin. And the temperature drops to 7 degrees C. This is going to be T2, which will be 273 plus 7 is 280, 280 Kelvin. So this is T2, this is T1. And so volume didn't change, see? So the volume didn't change, we'll cancel that out. And then we're solving for the pressure, P2. So P2 is equal to T2 over T1 times P1. And so plug that in. T2 is 280. T1 is 298 Kelvin. And P1 is 3.67 atmospheres. To what quantity will the pressure change? So they're asking for the, not the final pressure, but they're asking for the pressure change. And so we need one more step here. So the pressure, the final pressure is going to be 280 times 3.67 divided by 298. And so the final pressure is 3.448 atmospheres. So we start off at 3.67, we end up at 3.448. So what was the change? Well, the change is we lost some, so minus 3.67. And the change in pressure was minus 0.221 atmospheres. So we lost 0.221 atmospheres in the pressure. if we subtract those two numbers. So let's see what how they did this here. All right. I guess they should say to what quantity will the pressure change to. So I was thinking they're asking what the temperature of the pressure change was, which was a drop of 0.221 atmospheres. But it looks like they just want to know what the final pressure is, which is 3.448 atmospheres or 3.45 atmospheres. Well, anyway, we're out of time. And so we may look, this is actually the last problem is number 67, but we may look at a couple of STP problems. But that's it for this chapter, almost. Okay, all right, thanks. We'll see you guys tomorrow. If there are any questions, let me know. Bye now. Thank you.